Hey guys, welcome to my channel. This is Bharat, and this is a series of videos on heat transfer. Today we're going to study about convection. Convection is essentially a process of heat transport effected by the circulation or mixing of a fluid medium, which may be gas, a liquid, or a powdery substance. So much, huh? This is a mechanism of heat transfer through a fluid in presence of bulk fluid motion. The heat transfer happens here because of the fluid motion. So the convection is classified into two: free and forced convections. What are free and what is forced? Look at this example here. The air currents which are generated in this vessel are natural, are generated naturally. There is no other external agent which is generating these things. How they are generated? They are generated because of the temperature gradient exists in this region. So the hot air gets lighter and their density decreases when they get heated. So they move upward, and the warm and more dense air will come down and fill this gap. This is all happening because of the gravity. So free convection is a natural process. Designers of furnace, house heating systems, architectural projects, roads and concrete structures will be concerned with free convection. In the cases like when we have to provide heat dissipation for equipment in space or in some satellite, we cannot use free convection in that case because there is no air there. So in that cases we may rely on other methods. Forced convection, maybe flowing on the fluid over the electronic devices there. Yeah, that may be a solution. So in this lecture we're going to cover some of the fundamentals for studying about free convection. So before studying convection in more detail or heat transfer in more detail, we need to have some background in fluid mechanics too. So let's recall what is laminar turbulent flow. So laminar flow, in this flow the streamlines go in a parallel manner, like they don't intersect with each other. And we can predict the motion. In case of turbulent, the streamlines intersect with each other, something like a crowd in railway station. It's a good analogy of what is turbulent flow is. So there is a scientist called Reynolds, and he conformed these two regimes in fluid mechanics. And his investigations revealed the nature of fluid flow is governed by the following parameters: mean flow velocity, density of the fluid, dynamic viscosity, and the characteristic dimension. Suppose what is characteristic dimension? Consider a pipe, then the characteristic dimension of that pipe is its diameter. I will explain in more detail what is characteristic dimension in a minute. So the Reynolds number then becomes rho Vd by mu. You can also interpret it as an inertial forces by viscous forces. So if the Reynolds number is high, we have more inertia forces. So the flow will be turbulent. When the viscous forces is when we have viscous forces more, that means less Reynolds number, the flow will be laminar. There is also a what we call it as a so if the Reynolds number is up to 2300, then we can call it as a laminar. If it is between 2300 to 6000, we call it as a transient flow, which is conversion from laminar to turbulent. If it is above 6000, we'll call it as turbulent flow. So I told you before about characteristic dimension. If you do in the case of pipe, we take its diameter as the characteristic dimension. So what if we have a rectangular, dirt, or any other annular shape or any other shape? So there is a formula for that. Equivalent diameter equals to 4 times the cross sectional area by perimeter, weighted perimeter. Suppose consider this rectangular dirt with side A and B. So its cross-sectional area is A into B and its perimeter is 2 into A plus B. So 4 times area by perimeter, that gives you 2AB by 2A plus B. So this is a characteristic dimension of a rectangular duct with sides A and B. So this is about laminar and turbulent. Let's move on to Newton-Rickman's convection rate equation. So the adjusted fluid can be prescribed by, this is also called as Newton's law of cooling, where Q equal to HA delta T. I think in the equation provided below there is no A, and this Q is small q, that means it's capital Q by A. So yeah, this is heat flux. We are talking about heat flux means heat by area. So we can call it as Q equal to HA delta T. So what is this H here? H is called as coefficient of heat transfer, or surface conductance, or film coefficient. The values of film coefficient H is dependent upon surface conditions, means the surface may be rough or smooth, geometry and orientation, like the plate or the hard object, maybe a plate, maybe a cylinder, maybe something other shape, and thermophysical properties of the fluid, like heat capacity, specific heat capacity, thermal conductivity, density, viscosity, and other things. Nature of fluid flow. The flow of the fluid is laminar or turbulent. This also affects the H parameter. Boundary layer configurations and prevailing thermal conditions. So in the whole of this series, the main concern of ours is to find the H. We will be dealing most of the problems to finding H. So that would be interesting. So next is Nozzle number. Nozzle number. Before explaining Nozzle number, consider this scenario: heated wall surface at temperature Ts, which is shown here, and we have a fluid flowing over it with a velocity u infinity and a temperature T infinity. So the layer which is just above this heated surface adheres to the surface because of the viscous forces, and there will be a velocity gradient from the surface to the to a certain distance from the surface. So we call that that layer as a hydrodynamic boundary layer, and it is defined as a distance y from plate surface at which the velocity approaches 99% of the stream velocity. So the thickness is distance y from this plate at which the velocity of the stream is 99% of the free stream velocity, that is 99% of u infinity. In the same way, there also exists a thermal gradient because the temperature of plate is Ts and the temperature of fluid is T infinity. So this difference will create a thermal gradient here. So this is also having a thermal boundary layer will also have a thickness which is equals to the height y from the plate, where the temperature becomes 99% of the free stream temperature. So at the plate surface, there is no fluid motion and the energy transport can occur only by convection. From energy balance, this heat transport must be equal to heat transferred by convection to the rest of the fluid. So at the plate surface, where y equal to 0, the conducted heat is this, and the heat transfer to the fluid surface is this. We are equating these two things. On rearranging the above equation, we will get this. Now, if we know this thermal gradient at y equal to 0, we can find H, right? Now we will introduce a characteristic less dimensional into this equation. H L by K. We'll just multiply this equation with L and divided by K. We can rewrite the equation like this, and again we can rewrite the above equation like this. So this dimensionless parameter H L by K is called Nozzle number. Apparently, Nozzle number may be interpreted as a ratio of temperature gradient at the surface to the overall reference temperature gradient. The parameter here, we call it as it is a dimensionless slope of temperature distribution curve at the surface. Oh, lot of information, but no, I didn't understand anything. Like, let me explain. Consider this Nozzle number as a ratio of heat transfer due to convection by heat transfer due to convection. If the Nozzle number is more, we will have more heat transfer due to convection. If Nozzle number is less, we will have more heat transfer due to convection. That's it. Very easy. Yeah. Now we're gonna study one of the most important mathematical skill for heat transfer. That is Beckham's-Spy theorem. So, if there are n variables in a dimensionless homogeneous equation, and if these variables contain m primary dimensions, and then the variables can be grouped into n minus m non-dimensional groups, and we call these groups we call these dimensionless groups as pi terms. For example, consider this function. The resistance R experienced by a partially submerged body depends upon the velocity, length of the body, viscosity of the fluid, and density of the fluid, and the gravitational acceleration. So this is a function of that 6 parameters. When we reduce them dimensionally using into fundamental quantities. By the way, we have 5 fundamental quantities in this analysis. As you know, 3 of them will be mass, length, and time. The other 2 are temperature and heat. We represent temperature by theta and heat by h. So, as per Beckham's-Spy theorem, we have to we have to take physical quantities. I have to take a difference of physical quantities and fundamental quantities. So there are 6 physical quantities here, and we are using only 3 fundamental quantities to represent them. So we have to do a subtraction here. 6 minus 3 is 3. So they will be we can rewrite the above equation by using 3 pi terms. So now we have another task is to choose our core group. We will by experience, it is very suggested to use length, density or viscosity or velocity, thermal conductivity as a part of our core group. So here we need 3 pi terms here. So we choose length, velocity, and density as a part of our core group. So after choosing core group, we will represent our first pi term as L, length power A, core group elements power A, B, C, and other remaining element without any power, and we reduce them to dimensions. And now if you take the equations like this, like for m, the power of m in this case is C, and this case is 1, so C plus 1 equal to 0, and C becomes minus 1. Similarly, we will solve for L and T, and we will obtain powers of these 3 terms here, and we place them, and we will get our first pi term. In a similar manner, we will get our second and third pi terms here in this way. Now we will place that in this equation. Rearranging the above equation, we will by taking the R into left hand side and remaining parts into right hand side, we will obtain the equation like this. After taking common of rho v square L square, we will obtain 2 terms here. Actually, they must be multiplied. They are 2 terms here. So it seems like the function has only 2 parameters here, which is Reynolds number and Prandtl number. So they too are also a most famous dimensionless groups. So in this way, we're going to convert this dimensional Beckham's-Spy theorem will help us to condense these equations into dimensionless condense the equations into dimensionless functions. Like we have converted here this function into this which has parameters has dimensionless parameters. Why do we, in the first place, why do we do this conversion? We do this conversion because in practical usage of these terms, practical usage of these formulas, in experiments we will encounter a lot of errors, measurement or any other errors. So to overcome that errors, we should definitely use dimensionless numbers. To reduce that impact over the results, we have to use the dimensionless number. So we are using Buckingham's pi theorem to convert each and every phenomena. We want to express every phenomena in terms of these dimensionless numbers. So there are many dimensionless numbers, but we will consider only 4 as of now. I explained you about Reynolds and Nozzle numbers already. So what is Grashof number and Prandtl number? Grashof indicates the relative strength of buoyant to the viscous forces. In the formula, of course, it shows buoyant force into inertia force by viscous forces raised power 2. Grashof number has a role in free convection, similar to that played by the Reynolds in forced convection. Free convection is usually suppressed at significantly low small Grashofs. If you have a small Grashof number, there will be less free convection, and there will be less movement of air, so movement of fluid, so there will be less free convection. If you have more Grashof number, we will be having more movement in the we will be having more naturally formed currents, so we'll be having more free convection. So what is Prandtl number? Prandtl number is an indicator of relative ability of the fluid to diffuse momentum and internal energy by molecular mechanisms. Basically, it is kinematic viscosity by thermal diffusibility. This is shown in this formula, V by alpha. So apparently Prandtl is the kinematic viscosity indicates the momentum transport by molecular friction, and thermal diffusibility represents the heat energy transport through conduction. So for highly viscous oils, we will be having quite a large Prandtl number, like 100 to 10,000, because they will be having more viscosity, so we'll be having more Prandtl number. The Prandtl number is connecting link between velocity field and temperature field, and its value strongly influence relative growth of velocity and thermal boundary layers. We talked about boundary layers in the previous slide. I will just show you. I think I can show you that. Yeah, this is a hydrodynamic boundary layer and this thermal boundary layer. The thickness of these two are linked by Prandtl number. I will show you that too. That there is an equation. So this is the equation that relates those two. The thickness of hydrodynamic boundary layer by the thickness of thermal boundary layer is approximately equals to Prandtl power raised power n. Where n is a positive coefficient that will be changing from fluid to fluid. So yeah, this is a finishing. If you like my video, please like, share and subscribe to my channel. Thank you.